Alrighty, welcome back everyone. So today we're going to finish up the multivariate linear regression and go through the mathematics behind it and the actual code. I think you'll like both quite a bit. The math is really neat and it sets the stage for what we're going to be doing later on. So sit back, enjoy, and we're going to kind of drop in where we stopped on the last one, which was where we had a new cost function. So let's talk about that before we jump into the new stuff. So we said that we had a new cost function, which was our j, which was theta. We'll just call that for right now. We had 1 over 2m summation I from 1 to m of, we're going to have bracket h of xi and then minus yi, and then all of that was squared, right? That's the MSE. Oops, where's my closing parentheses? It should be right here, right? Because it's a function right there. Now, the difference that we run into is right here in this x variable, because it's no longer this x is not a single x. So this hypothesis function looks like this. We have h of x now is going to include all of our features and the parameters that are associated with them. So we're going to have theta sub 0, x sub 0, plus theta sub 1, x sub 1, plus theta sub 2, x sub 2, plus theta sub 3, x sub 3, plus theta sub 4, x sub 4. All right, those are 4s, I promise. So we have, this is for our new hypothesis function where, again, our x naught is going to have a value of 1. So that the theta 0 parameter is going to be our offset. It will be the y-intercept when we fit our linear model. So this, though, as we talked about, is a really inefficient way of coding it. And so we used a little bit of algebra, and we said that we're going to instead just have a theta vector. I have a cat trying to get into my lap right now. No, kitty, not now. So that holds theta 0, and the cat jumped up in any ways. You can, see the cat. If you're going to be up there, at least say hello to the camera. There you go. Okay, so let's try to ignore the cat. Hopefully she won't get in my way too much. So we have theta sub 0, theta sub 1, theta 2, theta 3, and finally theta 4. Okay, and then we had for our x variable, it was also going to be a vector, and it was x0, x1, x2, x3, x4. And so we used the linear algebra to rewrite this really compactly. It's just saying h of x, it's just now going to be equal to theta transpose x, where you would transpose the theta vector, the column vector, turn it into a row vector, and then just do the linear algebra multiplication with the x column vector, and you get exactly what we have here. 100% the same. It's just in a much better compact representation right here. This is an excellent form. Alrighty, so this is our cost function, but this hypothesis function that's kind of built inside of it right here, it has all of these parameters and features built in. So I'm going to expand this. I'm going to have to write a little small because there's no way I'm going to get it on otherwise. So I'm going to say j of theta is equal to 1 over 2m summation I from 1 to m of, here we go, big bracket, paren. Sorry, this is what we have to do. Theta 0, x 0, and this is the ix, and then it's plus theta 1, x 1, I, plus theta 2, x 2, I, plus theta 3x3 I think I'm going to make it, plus theta 4x 4I. Hey, I think I'm going to. Awesome. And then that's minus y I. Alrighty. Bracket and square. That was beautiful. So this gives us our y hat predicted value, and then we subtract off the actual value, and that's how we get how far our guess is from the actual value, which we then square and then average and all of that so that we get the MSE. So this is what our new cost function looks like with the theta transpose x expanded inside of it. Alrighty, so that is the cost function. Lost my mind for a second. But what we're heading towards is to be able to update gradient descent, right? So gradient descent uses, let me actually see, I think I'm trying to remember if it's the next slide or not. Yeah, I think we're good. I think we're good right there. So for gradient descent, remember we have the algorithm where we have, it is calling the derivative of the cost function with respect to a theta. In the old version, it was just with respect to theta 1. That's the only variable that we had for the single variable linear regression. But now theta takes multiple values. There's a theta 0, theta 1, 2, 3, and 4. So we're going to work it out, 2 examples, and then where it's theta 0 and theta 1, and then we should see a pattern that we can apply to theta 2, 3, and 4. Okay, so let's knock that out. So let's do this partial derivative with respect to theta 0. Now, since we're doing the partial derivative, theta 0 is the only variable that we're doing, that we're inside of this expression. All the other thetas are constants. Well, as all the other variables are constants, right? The x's and everything, the y, all of that is a constant when you're doing with respect to theta 0. Okay, so this is the only variable inside this expression when we do the partial derivative of this expression with respect to theta 0. Okay, so what do we get? Well, we get the 1 over 2m, like before, summation I from 1 to m, and here we go. This is going to be a chain rule that's going to kick in, very similar to what we saw before. It's going to be, this whole thing is raised to the second power, so it becomes 2 times this whole thing in here, right? So this is going to be theta 0 x 0. I'm only going to do this once, so you don't have to worry about that. Theta 1 x1 I plus theta 2 x2 I plus theta 3 x3 I plus theta 4 x4 I. Okay, so this right here, oops, I forgot my minus yi. Ooh, can't do that. Kind of need that. It won't work without it. All right, so minus yi bracket. So the derivative is going to be 2 times all of this, and then we'll subtract 1 from the power. So this will be to the first, which is just it. Now we have to multiply this by the derivative of the interior, where theta 0 is the only variable inside of here. Well, when we do that, all of these are constants, so they go away. They disappear completely. The only thing that's left is we have x sub 0 I times the theta 0. If I take the derivative with respect to theta 0, all I'm left with is x sub 0 I. It's supposed to be an I promise. promise. Alrighty, that looks weird, but I'm going to leave it. So this right here is the partial of the cost function with respect to theta 0. I can write it a lot more compactly if I want to. These 2's are going to cancel, right? That's why we did it 1 over 2m in the first place. This is going to become 1 over m summation I. My eyes are not picking up correctly. 1 to m of, well, all of this is just the h of x, right? So this is h of x I, and then minus yi, bracket, times x sub 0 I. Okay, so that is the partial of j with respect to theta 0. This is what we get right here. Alrighty. Now let's do the partial with respect to theta 1 and see what we get. So I'm going to erase a good amount of this up top. I think y'all are okay if I erase this stuff. I'm just going to leave the cost function down below. Make it a little bit larger. I don't want to erase much. I can take all of this. Just have to be careful on the right as I close the cost function. I don't want to touch it. Okay. So now let's do the partial of j with respect to theta 1. Alrighty. Well, what changes? Almost nothing changes. It's still going to be 2 times the interior untouched to the first power. What changes is what it gets multiplied by. So let me write that out. This is 1 over m summation I from 1 to m of bracket h x I minus y I bracket times, now what does it get multiplied by? Well, when I take the derivative of all of this stuff on the interior with respect to theta 1, the only thing that survives is x of 1. So x of 1 I. There you go. So this is kind of nice because what this means is every time I take the partial derivative with respect to a specific theta, the x that is paired with that theta is what I wind up multiplying this expression with every time. Theta 2 would be x of 2. Theta 3 would be x of 3, etc. So now I can actually kind of write all this up. Okay, so what I'm going to have for my gradient descent is going to be, I'll have my theta sub j. Yes, now we're going to be going through all of j is equal to theta sub j minus alpha times, here we go, 1 over m, this is the partial derivative part, summation I from 1 to m of h xi minus yi times x sub j I. Boom. There we go. That's it right there. This will update your gradient descent for each of the thetas one by one. And you call the exact same bit of code. You do it inside of a J loop now, where it's going to loop through all of the thetas, 0 through 4 in the case that we have down here. And it will just update as it goes. Now, the only thing that we need to be careful of, we already know that when we talked previously, we can't just assign theta 0, the new theta 0 to the old theta 0, and then calculate theta 1, because theta 1 will be calling the old theta, trying to use the old theta 0. Let me rephrase if I say that one more time. The new theta 1 will try to call the old theta 0 but it's already been changed if I do it like this. So I don't use this. What I do instead is I do temp sub j, gets all of these, and then once I have assigned all of the values to the temp block, then I assign all the temp values into the new theta. So the next step would be theta sub j's get temp sub j, and that's it. That's we're done. That is the entirety of the multivariate linear regression. You have to be a little bit careful with how you do your derivative, but once you do a derivative, you see that it's exactly the same thing that we got when we did the single parameter, except now we just have to cycle through j, where j is going to have the number of features that we're working with. And so we then have to assign all of the gradient steps to a temp block. And then once we have done all of those, we then assign all of the temp values to the new theta values as a block. And then we just repeat the process over and over and over. Now, turns out this is not easy. This takes a while. The reason that this can take a while is that as it's trying to find the best possible fit, the lowest cost associated, it's going to be bouncing all over the place. We kind of saw that if you had a bowl shape with two parameters, that it might start here and then it would meander a little bit and do like that and maybe go over here. And now extrapolate that to multi-dimensional space. You not only have something that is not guaranteed to be convex and have a global minimum. Well, it has a global minimum. You just won't be able to find it per chance if you don't set your initial conditions where it just happens to hit the global as it moves on down. But I think I said that right. It takes forever because now it is moving and updating in multi-dimensional space. So what we're going to do next is actually dive into the code and the solution to this. Alrighty, so here we go. Let me go to the new code, the new slide. That looks good. All right, here we go with the code. Yay, it worked. All right. So from here on, I know you're going to be a little disappointed. We are not going to be coding the algorithms from scratch. I'll be going over the details that are in the code because they're important to understand what each one of them is doing. That's the only way to really get a handle on what's going on for the actual models. You have to know what's going on with the cost function, the hypothesis function, all of that you have to know. Otherwise, you're going to wind up getting some weird results potentially, or not be able to adjust things on the fly if you start to get some strange results. So we're going to be calling our very first library calls, and we're going to be using pre-existing libraries that have been optimized to handle all of these things behind the scenes very efficiently, much more efficiently than I could code it up. I'm an amateur at best when it comes to coding. I've dabbled in it enough years where I can get in trouble with it, but I'm not an efficient coder at all. Ask anyone who I've ever coded something for, they'll tell you I'm a brute force kind of person when it comes to code. So we're going to be calling our models from here on using different libraries that people have written. They are extremely robust. They are awesome, and they're a lot of fun because it takes the drudgery of, I shouldn't say drudgery, it takes the uncertainty of coding your own code. You don't even know a lot of times if it's working correctly at the beginning because it's doing so many things. If there's a single logic error in anything, you may not be getting the right answer. But the libraries that you call have been vetted pretty well. So that's what we're going to be doing from here on. And I'm insanely excited that y'all get to start doing this, because this is where machine learning starts to really shine. This is the big hurdle that people run into if they start doing machine learning on their own, is that they start doing the function calls and everything from the libraries, but they're not solid on what's going on behind the scenes. By stepping through step by step with what's going on with the gradient descent, the calls function, all that stuff, y'all know exactly what's going on. So the calls are just making sure that everything's going to be handled efficiently. Um, but you've already done the hard work. So, um, congratulations, we are here. So, let me walk through this a little bit. We'll start off first thing with, we're going to be calling something called pandas. So, what is pandas? Well, pandas, it's just an amazing, helpful tool that was coded up to allow people to read in data sets that weren't necessarily all numeric. It can be all numeric. That's what our data set that I made up from scratch here is going to do. It's completely numeric, but it doesn't have to be. It can be uh, actual what's the word, qualitative variables. Oh boy, I hope I got that right. But it could be things like yes, 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 no, no, yes, yes, maybe, maybe, yes, yes, no inside your column of data. And it handles um, the non-numeric data beautifully. And so we're going to store our data in something called a data frame. And a data frame is, you can think of it as, it's really just an incredibly easy to use spreadsheet. And so you're able to take your data and import it into this data frame, put it inside the data frame, and the data frame will have everything organized kind of like you can imagine a spreadsheet, a virtual spreadsheet. And so you're able to then call specific columns and things with inside the data frame in your code super, super, super easily, okay, in a way that actually makes sense. So we're going to be using the data frame. And the next thing that we're going to work with is we are going to be using sklearn. Oh, I love sklearn. So sklearn, which is short for scikit-learn, it is a library that is just chock full of any kind of predictive models. You've got your linear models, you have your logistic models, you have all the regression things that you can imagine to do. Um, Anything that you've ever done inside of a course with predictive analytics, where you were trying to look at your data using a lot of analytical tools, it's in sklearn somewhere. It's just an extremely nice library full of tools that people have already coded. Um, Now, what we're going to be doing is we're going to be calling the piece, the tool inside of sklearn called a linear model. And the linear model is just, it's used for um, basically fitting data. And I shouldn't say it's just for fitting, because it can be used for single variable regression, multivariate regression, and even logistic regression with some alterations. So it's a really robust model that we can use. We can call, feed in our data to it. It will then run through the process behind the scenes of what we've already been working on, which is, the cost function, the hypothesis, all that stuff, gradient descent, and it will fit the data to the best possible fit using that type of algorithm. Okay. And then we get to examine the results, and that's it. So as you can see, it's super compact code, and I'm going to walk through it just a little bit. So The coef right here is just going to hold the coefficients for um, our parameters when we fit the data. It's going to hold all the theta zeros, theta ones, etc. So that's what coef is going to hold. And this just means it's going to hold it in a list. Coefficient 0, coefficient 1, coefficient 2, etc. as a list. Okay. Now this right here is data that I completely made up myself. I didn't pull it from anywhere because I wanted to use the same thing that we've been working through with the regressions. It's single variable, two variable, and now multivariate. This is what we were talking about. I matched up the examples that we did, and I just extended them a little bit with more training examples. So the size of the house in square feet, the number of bedrooms, the number of floors, the age of the house, and then the price in thousands. Okay. Um, so, like I said, I made this data up. I literally took a sheet of paper and I wrote out what I thought each house would be worth given the number of bedrooms, floor size, and the age of the house. And so it's not going to be a perfect data set because I made it up, but it holds together pretty well. All right, so we're going to read in all of this data and store it in a variable called house features. Then we're going to read house features into a data frame. We're going to put it inside of a spreadsheet. And this is where the data frame absolutely shines. It is so wonderful, so easy to work with. We're going to store everything, the data frame that we're generating, in a variable called df. That is just standard. If you're only doing one data frame assignment, typically inside of Python code, you're going to see that assigned as a df. Doesn't have to be. It could be anything. You could call it spreadsheet or whatever you wanted to, but df is typically what you're going to see in a lot of code. So the data frame is going to receive from house features, which is where we have all of our data stored, the following columns. So the way that this is set up is that size contains all of this data, numbr contains all of this data, and so forth. And so what we're going to set to what we're doing here is we are going to assign inside of our spreadsheet columns that are going to start with size as a header, numbr, numfloors, age, and price. And each one of those is going to have the data stored underneath them. So these are going to be the headers of our spreadsheet in our data frame, the actual column headers, and the actual values are going to be below those. Alrighty, so all of that is now stored in a nice, neat little spreadsheet called df. Okay, and we can access this data so elegantly. This is so nice. I can't say how nice this is, that all you have to do now that you've stored it all in the spreadsheet is just take that data and assign it into your X variable, which is going to hold all of your features, and the Y variable, which is your outputs. So the X variable is going to be getting the data that includes size as a header, number BR as a header, number of floors as a header, and age as a header. So it gets all the data for those 4 columns inside of our spreadsheet. That's what gets stored in the X variable for our features. Then the price gets stored, all that data, in the Y value. That's it. That's all we have to do. We have now loaded all of the data in all the feature data in our X variable and all of the output, the prices, in our Y variable. So now all we have to do is call the model. When data is ready to go, we just need to call the model, feed it the data, and then see what we get. So we're going to call the linear model that we imported above. We're looking for a linear regression. So it's going to take that model and store it in regra, the variable regra. This is something that I don't think you've seen before. You may have seen it somewhere else, but this is the first time I think we're doing it. This is one of the really nice features of Python, is that what it allows you to abstract things to where they make sense kind of in an English way of thinking about it. What's going on here is I'm taking the full model, the linear regression model that's located inside of the linear model that I called up here, and I'm assigning that model to a variable called regra. Regra now has that entire linear regression model ready to go. Then all I have to do is call a method within that model to actually do something. So I then do regra fit on my x and y, and it does the linear regression fit function on my data, where the x holds the features and the y holds the outputs, the actual prices. Okay, this right here, these two lines are it. I assigned the linear regression model to a variable, then I called that variable and fit my data using the linear regression model. That's it. That did all the work for us. And so now I'm going to be pulling out of that some of the results so I can print them down. But before I do that, let's actually run this and see how fast it is. So here we go, running and done. It's just ridiculously fast. It's not a lot of data here, but it's still ridiculously fast. Even if these were 10,000 training examples with 10 features each, it's still going to be fast. It's a very efficient model, way better than what I would be able to get. So the output is over here, and we can see that we have, I hope y'all can see, I hope it's not too like squished for you to see it. So we have an R squared value, which we got out by doing the score that was output by the regra fit. And so the R squared is 0.91, which means it did a pretty good job fitting that data. That's a nice high value. 0 means it did a terrible job of fitting the data. 1 is a perfect fit. 91%, I'll take that and run with it. So I tend to believe that with an R squared of 0.91, that the actual parameter values are probably going to be pretty close to what they should be. So we then have the output here. The price is determined by the size, which times 0.09. Well, now the price is in thousands. So if I multiply 0.09 by 1,000, that is saying that the size of the house times 0.09 times 1,000, so the size times 90, which means that every square foot is worth $90 in the price. Okay, the number of bedrooms is worth $54,000 each. That's what the final price is decided by. So that kind of makes sense. The more bedrooms, the higher the price goes. The number of floors, which I was a little bit surprised by, wasn't, of course, I made up the data. In the real world, maybe this would be a lot more indicative or influential with the price. But in my world, my data, it is worth, each additional floor is worth about 7,000, so $6,700. Now this one I like a lot because the age should be a negative parameter, because as the house's age increase, the price should go down. So this says that every year of the age of the house reduces the final price by $3,000, which I'd say that's probably pretty accurate. So there you go. That's how we did all this. And these values that we pulled out, I guess the R score were the values that we got from the fit here, and then the coefficients got all the values from regra.coefficient or coef underscore. There's an underscore here, so if you try to pull these out yourself, make sure you note that this underscore goes with the coef. And so then I just called them one by one: R score, coefficients of 0, coefficients of 1, 2, and 3. And that's how I got all these values over here. And that's it. So I hope you have enjoyed this. It's just insanely nice. If you know what, I will do that real quick. If I change the price, maybe this one goes to 40, and this one goes to 350, maybe, and run it again. Yeah, my R squared now is not quite as good of a fit, and it changed some of the values. Looks like the number of floors went up quite a bit, and the age didn't affect things as much. So there you go. You can play around with this, with the features and the prices, and see, how it affects your model if you want to. Um, so the next thing that we're going to do is logistic regression, where we'll actually be trying to sort data into binary categories. So I think you're going to enjoy that one a lot. Now that we're going to be getting away from predictive land and going into actual classifying land. So I guess that's about it. Y'all have a wonderful one, and I will see you later. Bye, everyone.